Hi everyone, my name is Tang from QCRI. Today I will present Symphony, our vision system towards supporting natural language queries over multimodality data lakes. And this is a collaboration between Tsinghua Renmin from China and also Arizona MIT from US. For multimodality data lakes, generally we refer to a collection of data with different formats like CSV file, text files, databases, and so on. The first is this kind of data lakes are very common for many organizations. You can think about a lot of applications like data discovery, data acquisition to find data to train machine learning models. But at the same time, how to query and explore such data lakes is a hard problem. So this is one driving application we are working with PSA. So PSA represents Qatar Planning and Statistical Authority. Basically, is a government authority, collects all the data from Qatar. And after they collect data, they publish some data on the web so people can browse and download. So the problem is this is a collection of data with different format. And oftentimes it's very hard for people to do the eyeballing to download the one data set that they need. So far they only have this data request portal that you can input your name, email, and also the natural language request on the bottom right about what data set do you want. And this will be sent back to PSA. This will take 5 to 6 working days, 3 people's manual work to find data set and send back. So this is very low efficiency. So what they are trying to work with us is about how to build a chatbot to replace this manual work to find the data set they need and ask simple analytical questions, right? So before I present the vision of Symphony, let's see why existing solutions are not enough to support this kind of applications. So from data management perspective, so oftentimes we want to support structured query like a SQL. But if we want to support SQL queries in data lakes, we have to go through this data preparation, data curation with ETL, cleaning, schema matching, dedupe, all these operations. And this is known to be very time consuming. Especially for this situation that data come every day in different formats and also without any predefined schema and metadata. So this will take forever. So what we decided to do is we cannot afford to do data preparation for this data lake. We just dump the data and index there. Right? The second is because we don't have data preparation and data with different modalities, we cannot support SQL queries. So instead, the most natural way to support is natural language queries. Right, so now the vision is we want to support natural language queries on top of a collection of data with different modalities. And this is the overview of Symphony. So it's a retrieval-based model that given any natural language query, so the first step is to retrieve the documents, maybe a text file and the CSV file that are relevant to the query. And then we have a reasoning model that given this data set that can answer the query, how to do the reasoning to answer this query. Okay. So of course, because it's natural language and you think about machine learning models or language models. So next question is, why not just use foundation models, right? Because foundation models is so powerful that they already learn all the data from the web, with different format. So foundation models store all the information in its parameters or neurons. You can consider this as implicit knowledge. So there are 2 problems. First is it's very poor for reasoning, especially for database-like reasoning. So for example, already foundation models can already read those tables. You cannot ask joins, you cannot ask aggregation of certain table, it's not there. So in Symphony, so we store the data as explicit knowledge. So during retrieval time, you always need to find your data to do visualization and update time. And another problem is about update. So foundation models were updated very slowly. Basically, for GPT-3 is released every 6 months, and they cannot contain the up-to-date information. So now assume you have a question about, so someone gave an interesting talk about the Dutch tomatoes in CIDR 2023, but you don't know who gave the talk, but you don't know the content of the talk. So the data is there, right? But the data image, the text information. So if you want to use foundation model to answer the question, you have to retrain the model. And the retrain the model is extremely expensive because it contains 100 billion parameters. So we cannot afford to do that. So by doing that, by doing the Symphony way, we just dump the file there. So without changing of any reasoning model. So during the reasoning time, if you have these questions, we can retrieve this document, and any existing NLP QA question answering model can answer the question by extracting the name Professor Alonso from this. Okay. So basically, Symphony aims to tackle the problem that cannot be well supported by existing systems. So let's walk through one running example. So we have the data lake. I'll talk about the index later. We index the data set with different modalities. Now, assume you have a query about which sounds appear in a film produced by its producer name and director name, right? So here we know that this can be answered by some data sets. So now we do the data retrieval part to find two data sets. The first one, the capital P1, is from Wikipedia. So it's a text file. The second one is a table. So here, so none of them can answer the question alone. You have to put them together to answer the question. So from the first text file, actually we can extract the name of the field, which is Farah, with this producer name and the director name. By knowing the name of the film, you can use the second table to write a SQL query to extract the name of songs, which field name equal to Farah, right? So we want to do this kind of reasoning, but the problem is it doesn't exist any model that you can give natural language queries and the data with different modalities to do the reasoning. So what we do is to do the query decomposition. The goal of decomposition is we try to decompose completed query into simpler queries, subqueries, such that each subquery can be evaluated on a single data source, right? Because for this one, we know how to answer the question. So for query decomposition, I'll talk about detail later. So basic idea is we can interact with foundation models. Here we interact with GPT-3 to say, hey, these are my data set, this is a question. Can you tell me how to decompose it? But this quite magically, foundation model can give us the answer. So if we ask the first question, this is the entire data set and the question. So foundation models can say, oh, the first sub-question should be, what is the name of the field? And you can evaluate this subquery on data P1, which is text data. And you can do this conversation with GPT-3 to say, hey, we already know the first sub-question, what will be the second sub-question? So GPT-3 will say, the second sub-question is what the name of the song in film, and using T1 answer it. Okay. So we use foundation model to decompose. And after this, we need to do the query evaluation. So you have the subquery, you have the data, you have somehow evaluate the natural language query on text data, natural language query on tablet data. And for this, we have some work, but also there is a lot of models about NLP over text data, NLP over tablet data. Okay. So this is a basic workflow of Symphony, right? For any queries, we retrieve multiple data sets, can answer this data set, can answer this query, and then do query decomposition, and then we do subquery evaluation, and then we aggregate the result of subqueries, get final result. Okay. So we have 4 steps. The first one is index. So basic idea is X to WAC. So we want to index any data sets to vector embeddings. I think many people talk about embeddings, and here, so we index text data, tables, databases. If they are too large, you can partition the tables, you can chunk text files into a much smaller size, and then you can use encoder to convert the data into embeddings. And then we use the index fact from Matter to index these vectors to support semantic search or vectors. The question is how to compute the encoder. So there are a lot of works, as you have mentioned, about how to compute the embedding of tablet data. So here we use a very simple yet effective and robust baseline called autoencoder. So the basic idea is if you have any data set, you can serialize as a sequence of tokens. You can train the transform-based encoder to compress the information into some vector representation. And this information is so rich, so it can remember many of the information of X. Such that you can use a decoder to reconstruct X from this information. So after we train this encoder model, we can remove the decoder, only use encoder here to encode data from different modalities into embedding. But this, so this is pretty well-known robust baseline, but there are many new works that you can replace this one. For the data retrieval part, it's very simple. Given any queries, we use pre-trained encoder to generate the embedding of the query, and then we use index to find top K result. And sometimes the top K, if the K is small, you cannot find a very good document. So sometimes we can enlarge number of K to, let's say, 10 documents, maybe 15, and we have human in the loop to say, oh, you should select some of them to answer the query. Okay. For the query decomposition, the problem is, given this natural language query PQ and the tabular data T1 and the document, let's say P1 in text file, how to decompose it? So GPT-3 you can consider as a human, and you can interact by conversations. And what we did is, so at the beginning we don't know whether it works or not, but when we tried it, it worked quite decently. So what we did is we generated prompts, the questions to GPT-3, and basically it's a template prompt. So we have the serialized text data, serialized table information, and then we ask questions based on the text and the table. Here's the question from user, which sounds appear in the field with this producer name and director name. So we asked GPT-3 how to break down this query into subqueries. And then GPT-3 can give the first subquery and then keep asking question, and GPT-3 can give the following question until it terminates. Okay. So this is workflow of how it works. So we have a template to generate initial prompt by giving all the information to GPT-3 to generate the first sub-question. And then we have a loop about next prompt, basically based on the previous prompt, how to generate the next prompt by interacting with GPT-3 until it says stop. Okay. So next one is a subquery execution module. So basically, so if the subquery is on a text document, so we use an NLP question answering module to extract information to answer it. If it natural language query is on a table database with several tables connected, we use NL2SQL module to answer it. But at the same time, there are other different modules. For example, NLDB is a work from Meta AI along Halevi's group. So basically, they want to do database-like reasoning over multiple texts. So you have each text called a factual text. You have a collection term, and you have questions, SPJ-like questions. They can answer this kind of question. And also there table QA. So the difference between NL2SQL and the table QA is you want to answer the same question, given natural language, given the table, how to get a result. So NL2SQL will generate the SQL queries, and then you execute the SQL queries on the table, the database. So table QA is different. You give the natural language query, and you give the table. There's just only one deep learning model to give the answer without generating SQL queries. So we have some papers, Tsinghua 23 on NL2SQL, and we just present a paper about table QA, ERMMP last month. So you can imagine that. So when you have different subqueries, you have different modules can be used. Naturally, you can think about the query optimizer. So that's something we are planning to work on. And because there's so many different modules, that's how the name Symphony came from. Because this is a visionary system, so and there's no benchmark on it, so we just show some proof of concept result. Sorry, I think skip this. So for the data lake, we index 400K web tables and also 6 million text files. And we manually design 18 queries. The purpose of designing this query is to guarantee this query can be answered by data from the data lake. For example, we can design queries can be answered by 2 text files, or the three tables, and the mix of tables and text files. So this query can be answered, right? So for the testing, we try to see manually check whether the decomposition is correct. Also, we also check whether the subquery evaluation is correct. So the final result is correct or not. So the good thing is there are 12 queries out of 18 are successful. That means for the query, we can get the correct answer at the end. So the example query is which is the tallest building in the UK or the tallest building in the South Korea, right? The first query. And by data retrieval, we can find 2 tables. One is about tall buildings in the UK, the other about tall building in the South Korea. And we can decompose the query into 2 queries. First one is kind of the height of the tallest building in the UK, the second one tallest building in South Korea. And we can extract the kind of the height of the buildings and we compare them to answer the query. But also we have some failure cases. The failure cases came from this kind of decomposed queries are not correct. But the good thing from this example is even you have failure cases, so the process is kind of interpretable. You understand what this model is trying to do. So in this case, given the query, so what year was the first German film that won Academy Award for Best Foreign Language Film released? So you'll see two documents. You'll see the efforts of the system of getting these two decomposed queries. Actually, if you understand how to debug it, right? So this could be a system that can assist you to debug the entire process and do some revision to still generate the correct result. So the failure case is, I mean, if you just run it, you don't get correct result, but you can interact to change some of them, the intermediate step to get correct result. So here's the conclusion. The first is Symphony is a new way of exploring multimodal data lakes, and it tries to solve the problem that cannot be well supported by existing solutions. And also the vision of Symphony, it will be AI assistant. It cannot be a fully automated system. And you can consider yourself as a political business leader surrounded by advisors. Right? These are the advisors can give you hint about you should do this or that. And the good thing is somehow interpretable. You can change the decision if you don't like it. And for the future work on one side, we're trying to build a system to deploy to work with the Qatar PSA. Research-wise, one thing we are trying to work is how to improve the indexing part is X2WAC. So the one hard thing is about how to align the embeddings across different modalities, because we know how to compute the embeddings of let's say text data or maybe image data, maybe tabular data, but how to align them is a hard problem. So one thing we are trying is we also do contrastive learning, but this contrastive learning is across different modalities. So we try to find similar examples from, let's say, the tuple and the text data. So this should have the similar embedding, not within the same modality. And also we are trying to combine the search of semantic using embeddings and traditional string semantic search. And for SubQuery execution models, already mentioned, we did some work recently for NL2SQL and table QA. I think one direction we are keep pushing in this direction after Sigma 23 paper. Thanks.